Sir.
Dear participants, we are expecting our expert in a couple of minutes. He will join immediately. Please wait. The topic, we are going to start the last session of today, third day of our ATAL FDP. The topic is Tele-operated robotics. Sir, good evening, sir.
Good.
Okay. Shall we start? Debanik, sir. Sir, good evening. Participants, just wait there. Some misunderstanding. The link was happened. Sir was logged in some other different link. Okay, so now within 2 minutes he will come back. Sorry for the inconvenience.
Okay, now you are doing correct. कौन कौन आ रहा है? मैं तो लेट ही बताऊंगी काम वाले मौसी से बात हो गई तुम्हारी बात मौसी से मैंने तो फोन दाई वाली मौसी जी को लगेगा गई हरिद्वार
Sir, welcome to the.
Yes. Good evening to
Yes, sir, good
everybody.
evening.
Yeah.
So I'm so sorry to the participants and the expert that actually some confusions was occurred in the link. Sir was joined in time, but unfortunately, what I have sent the link is the old link. Sorry, sir. Sorry for the.
No issue. Okay, these two happens in virtual things. That's the reason it is wiser to have some buffer time.
Okay.
So okay. So I think we should not waste much time. So let me start with my topic of
Yes, sir.
my lecture today, and let me just share the screen first.
Yes, sir. Please share.
Yeah. Is it visible to you, all of you?
Yes, sir. It's visible now.
Okay. So good evening to all participants for this FDP, and it is my pleasure to be with you this evening. And also I have thought of telling you something, some research story of me personally and of us from the scientists from Department of Atomic Energy, Government of India. And the topic of today's lecture is teleoperated robotics. So this is a kind of you can say a slow journey, which I will take you to the next 1 hour to 1.5 hours. And this journey is partly my own journey at Department of Atomic Energy, to be specific, Bhabha Atomic Research Center, Mumbai, and also some of the journey elements of my colleagues and other scientists as well. So I will slowly take you to that particular things. So essentially, this is application of robotics in nuclear industries, nuclear science and technology in general, and teleoperated robots and teleoperated robotics is a particular field of robotics which have been all over the world. In fact, not only in India, all over the world, it has been nourished by the nuclear scientists and technologists. And that is the reason in the outline I have mentioned two important keywords. One is IAEA, another is DAE India. DAE, of course, is our own Department of Atomic Energy, which comes under Government of India, direct under Prime Minister's office. And IAEA is the International Atomic Energy Agency in Vienna, Austria. So this is the body, maybe some of you are aware, but for other students and scholars, I can tell you this IAEA is a International Atomic Energy Agency body which was established after the Second World War to take care of the need of peaceful nuclear energy applications to various countries. And India is a participating country of IAEA and very promising country, in fact. So the whatever guideline IAEA generally gives to all of its member states, including India, and also some of our own need in India, we follow a guideline for teleoperated robots or teleoperated robotics for our application. So I will basically branch it out in 5 sections, and I will tell you that what are the R&D that we are doing and what are the futuristic attributes. So I will start my talk or details on the first section, which is remote handling technologies. And out of this remote handling, as the name suggests, that means you are doing something from a distance. And this distance is a very, very important part. This is not a small distance, not inside a room or something like that. Whatever generally happens in a laboratory, it is not like that. So it is a physical distance apart. Sometimes it is in quite a few meters also. And this distance is also hazardous. That means there is a possible chance of radiation hazard. And many times we are having a physical separation also, like wall, brick walls and lead shielding and all those things. So this is known as remote handling. And out of this technology, there are many technologies. Not all the things are robots. Today I will discuss mostly on the prime bread and butter of remote handling technologies of today's DAE is master-slave manipulators. Master-slave, as the name implies, there is a master robot, master manipulator, and there is a slave robot which will basically perform the duties of whatever master is telling it to do. So this is the way. That means slave generally operates in the hazardous areas inside the nuclear power plants or our waste disposal facilities, and whereas the master is comparatively at a safer location, and usually master is governed by a user, I mean kind of operator.
Excuse me, your PPT is not moving. We are actually.
No. I didn't move. I am in the second slide only.
It is the first slide shown on the screen itself.
Oh, you didn't. 1 minute. Let me just check it.
Because I think so. The master slave manipulation is there on the slide number 3. So that's why.
No. What I am telling, are you able to see this particular slide where it is written robotics in nuclear applications?
No, sir. We are able to see only the teleoperated robotics by you.
First slide, sir. It is in the first slide.
Is there only.
I do not know what I should do now. This one you have seen. This is being visible. This first
Screen is
my
visible,
name
sir.
and
Screen is visible.
Okay. Then I am doing the slide. Next slide. Is it visible?
No, sir. It's not moving.
So then it is. I cannot do much because I am sharing it. No. What should I do now? 1 minute. Let me just check it.
Full screen mode, sir. You put it on full
It
screen.
maybe the problem with the full screen mode. Is it visible now?
Now cursor is moving. Just sir, try to click on the second slide.
Yes, sir. Yes, sir.
No, but this is, I have clicked on the second slide only, but this is not in a full screen mode. This is just a kind of viewing.
You have to share the slideshow. You have shared
slideshow only. Otherwise, how can I get this? Even the first slide.
After starting the slideshow, you have to share, sir.
That is the reason. Otherwise, the first portion, this particular thing you could see, how you could see. This is why I shared the screen. But this moving part, I do not know what to be done. As you are telling, it is not moving. Now, is it visible?
Now it is moving. Now it is moving.
Okay, let it be like that. Let it be like that. Yeah? Okay. Pardon. Yes.
Okay, no problem, sir. Sir, but you will make it full screen first, then share your screen.
Then share the screen.
No. It is not.
Sir, press F5, sir. Press F5.
No. I mean, see. Is it visible?
Yes. Now it is
right now it is visible, sir. But when you convert it into the full screen mode, then it is not visible.
It is in full screen mode right now.
No.
Okay, sir. Carry on, sir.
Okay, carry on, sir. With this, carry on, sir.
Now, are you able to? Then, if you cannot see it, then there is no point in going forward. No, I mean, I am not getting what is the technical issue. See, right now in my laptop, this is in full screen mode and screen shared. Are you able to see this particular thing? This slide, can you see?
Full screen is not visible, sir. Actually, we are able to see the what we can say 4 slides over here and 1 slide as a main slide.
Then it is something with a bandwidth problem. I mean, that I
No,
can't
sir.
help much.
No, sir, it is not bandwidth. When you have supposed to show each and everything from your system, then you need to share everything, not only the presentation. You have to share
You have shared the
the
presentation.
entire computer.
You have shared the single video only.
Please listen to me. See, no. Once item is shared. I am giving the lecture every day or now and then. I do not know what is the problem you are telling.
Okay,
Anyway,
sir.
let me just come back to.
Without wasting much
No,
time,
I
sir.
mean, anyway,
just go
time is
ahead with
wasted
this.
already. I mean, I do not know. Like,
Yeah.
are you able to see
You
this thing?
go ahead with this, sir. You go ahead with this.
Is it okay now? Is it? Are you able to at least see something?
Yes, sir.
May
Yes,
not be
sir.
in the full screen.
Okay, sir.
I do not know what the problem actually you are facing. Maybe you are facing a problem, but from my side, I cannot do much. Anyway, so the second.
Sir, let it go. Just go
Yeah,
ahead.
I am going ahead. So second part is that after the master slave technology is established in India by Department of Atomic Energy during the late 1950s and then 60s also. Slowly we move to another group of remote handling technology with teleoperation, that is for serial and parallel robots for material handling. So those are our in-house developments. I will show you that some of the prototypes that has been made and futuristic part also. In last couple of years, around 6 to 7 years and little more than that, we have also done considerable effort in flexible robots, and these are for assistance and surveillance purposes, basically on-ground flexible robots. We have also done something on underwater things, but of course that doesn't come under the fully in the teleoperated robots. Just for your understanding, I have added. I will not dwell on it. And the next important chapter, which is very recent in our technologies for last 4 years to be very specific, is called sensor instrumented micro gripper, which is my own areas of research for telerobots and assistive robots. So slowly we have moved from telerobots to different assistive kind of robots. So we will do the things. Let us move to the telemanipulation and telerobotics, which is essentially all these robots are serial chain robots. And we have 6 different technologies that we have mastered. It is actually our full engineers technologies. So first, second technology, which is known as kinesthesia. Then fourth is telepresence, fifth haptic interface, and sixth is internet telerobotics. And in fact, all these things have been thematically derived from Dr. Homi Bhabha's wish actually. And he, as you know, he was the pioneer of peaceful utilization of nuclear energy in our country, and also he was a prominent figure at IAEA and other international bodies those days. And he also expected that with all these new technologies, that time robotics was not very much known, but remote handling technologies, telemanipulation, those things were known to the audience. So this is the first one of our technology, which is master slave manipulator, we call MSM. And this technology is today fully indigenous. I mean, that is, we are very proud to tell you that technology is fully indigenous over the years. Of course, there was a lot of struggle period. And even in the world also, it was first developed at France, and which was known as Ma Telerobot. And first Indian prototype was made in the 60s. And of course, we have taken a lot of input from this French telerobot, but the Indian one, which was a mechanical type master slave, the first ruggedized, kind of system. And of course, those things are not in use in Indian power reactors these days, but it was our glorious past, you can say. And all of the present 23 nuclear power reactors, they use master slave manipulators, which are totally made in India. So that is the kind of a structure that we are right now having. So this is a kind of a Tele manipulator where we have seen that structural things, and this is a kind of a quite a historic picture. This was the actual original sketch of Tele manipulator, the French one, and during those days, the drawing technologies were, of course, drawing board technology. And so I personally feel this is a kind of a historic picture which can be shown. Similarly, at the same time, more or less at the same time, during the French, kind of research, in US also, in Argon lab, there was a development made, and this is a kind of Argon lab slave manipulator that time was used. So there are some differences between this French and this US versions, and Indian version is more, I should say, linked to the French version, and we took significant input from the French version. This is the present version at DAE, these MSMs, and these three pictures are actually the development of the prototype that has been made fully in our workshops, and those are now in operation in nuclear power plants. So essentially, the idea is like master arm. There will be a master arm which is being handled by an operator, and there is a through tube, and there will be a kind of a slave arm which is inside the, you can say, the hazardous zone. We generally call it a hot cell, and hot doesn't mean it is a temperature wise. This is basically radiation hazard wise, and there is a viewing window through which we see whether the slave arm is doing the job imperfections. And if you look at these pictures, you will find that there are some kind of a peculiarity in the gripper part actually. So this gripper of the master slave manipulator, these are totally different from a normal robot gripper and wrist also. So those are the things where actually we feel it is the best one. Various configurations of master slave manipulators have been developed over the years in Department of Atomic Energy. Out of that, one interesting type is a gantry type, which was totally our own design, and gantry type was used for some specific applications in our waste disposal facilities, and this is one of the success story of ours. And there are a lot of R&D that went. Of course, it is easier to see by some slides, but actually there was these were big projects in the early 70s and 80s, and a lot of analysis and R&D went through. Whatever resources we used to have, we have to keep in mind that 70s, 80s are the very dreadful period for atomic energy, because we were under embargo. So we couldn't get any of the good softwares or hardware, of course, and everything was made primarily at our home. So all these analysis, like kinematic analysis, design, and those are very important for any mechanical system. Those were done by our own engineers and technologists. So this is the part. So that is the reason when we started from scratch. So today, this is a important kind of a milestone that we have achieved. And as I was mentioning, in MSM, various designs have been prototyped in the last 50 years. And we started with mechanical type MSM in 1955-75, this first 20 years of DAE's functioning. We moved on to something like a little more on robotic structures called articulated MSM, 80s and 90s, 1980 to 1990, roughly. We have another interesting thing during that time called servo manipulator, servo MSM. Of course, this was not prototype because this was having some kind of R&D use only, but we didn't use it in the nuclear power plant. Then the next important thing that went to power plant areas is called three-piece manipulator, three-piece MSM. 1995 to roughly 2002. And during that time, I am also a part of the family. So I have particularly seen the developments of 3-piece manipulator, 3-piece MSM. Then, of course, 3 to 4-piece. Not much of a difference technologically, but manufacturing-wise, there are a lot of things that we added during this thing. So that was the concept. And finally, in the recent past, around 2010-12, the hybrid MSM also came in the picture. So essentially, all these things, especially the hybrid one and the you can say 4-piece manipulator, they are more on robotics side actually. So we developed a lot of gear systems, gear motors, clutches, and all those things. So those things were there. But whereas the mechanical master slave manipulator, these are totally mechanical. There was nothing other than rope and structures. So those are the differences that actually happened. Yeah, so that's what I was mentioning. These are the initial days of MSM technology where this is pulley, rope, and all. And these are very difficult for kinematic analysis. Even in today's finite element softwares, etc., you will find it very difficult to model a rope or pulley, etc. So drive cables, wire rope, those are the technologies that was used, and those are very robust actually, very rugged, very robust. But at the same time, like it is difficult to have a good simulation beforehand. Next is the joystick technology. This is another very interesting technology that Department of Atomic Energy has developed, and in fact this technology was first experimented during 1990s at VARC with collaboration from Jadavpur University, Kolkata. And in fact I was a part of this program, and this technology was very universal technology. That means through a joystick kind of thing, or kind of a serial robot you can consider, even we can operate various configurations of slave manipulator. So that was the need of the hour during those times, that apart from master slave manipulators, we need some kind of a universal device that can control various small size robotic devices. So you have to consider that the way advent of robotics in atomic energy areas, nuclear power plant areas. So it is in the 1990s. That means many small robots have started, were thought of to be controlled, and joystick technology has a role in that. So I am just giving the glimpses because time is short. Now in the telepresence, the next technology that was experimented in the later part of 1990s, I think around 94, at Division of Remote Handling and Robotics, which is our primary division. So in BRC for robotics research, it was experimented, and we have very successful developments initially from the lab scale. Then we have advanced experiments with MSM around 2006 to 2009, as the right hand side photograph is showing. So a lot of advanced experiments we have done during that period actually. Haptic interface is another new technology that was developed with collaborations from IIT Kanpur, and that was also in the latter part of 1990, I think 96, 97 probably. And those were the days where we used to experiment, and there was some collaboration. And with collaboration, we could purchase, because collaboration was important for our procurement purpose, basically, to be very frank, because those days embargo was still going on actually. So we couldn't purchase many of the things as we thought of. Now there are many open problems even today also, as our young engineers and scientists join. So we do give them a lot of kind of a research problems actually. And see, one of the research areas where we need also good collaboration, modeling of cables and wire ropes, pulley of master slave manipulators, modeling of the wrist of the master slave manipulator. These are some of the areas where we need, or people should do very intense research. Modeling of serial chain joystick with chain sprocket mechanism, input of human factors in telepresence and haptic interface of master slave, and augmentation of software simulation with LabVIEW MATLAB. So these are the things that have been used in our arena, and we feel that this kind of a progress has to be made with the existing and known technology. So this is the area. Okay, so with the advent of master slave manipulators and the knowledge that was acquired for the remote handling technology, we started moving to a lot of serial and parallel robots for material handling, and we started moving to those developments of those robots. And these are all remote control based. So of course, initially we did a normal control system, but then we switched over to remote control. So this picture is showing a kind of a one of our initial developments in kind of a semi-gantry type robot, XY table, basically X, Y, and Z. And it is a spot picker robot. So it can take very, very small objects, and then it can go for image analysis and all those things. So those were developed during that time. One interesting chapter of Department of Atomic Energy's robotics research is with parallel manipulator, and there are a couple of indigenous technologies also that was developed in the division of remote handling and robotics during early 2010s under 10th and 11th 5-year plan. So generally, you know, we do the R&D in 5-year plan method. Of course, after 12th 5-year plan, there is no more 5-year plan now. But during those time, 10th and 11th 5-year plan was running, and this is one of the technology that was fully indigenous, and we developed a lot of R&D input through that. And in fact, those are well appreciated all over the country and world also. Another interesting serial parallel group robot is Cooperative Robot, which was done in the early 2000s under 10th 5-year plan, and it is also fully indigenous and in-house. And these indigenous things, I mean, you may find it very kind of a, you may be astonished, I should say. That means everything was bought and prepared in-house, starting from motor to encoder, and sometimes quite big inside, because we cannot procure those things in those days actually. So that was the, but it has given a lot of input to us. There was another remote handling, kind of a remote control, not remote handling, I should say, with the legged robot and walking machine, basically the hexapod, and it was in the early 1990s, sorry, late 1990s, under, I think, with IIT Bombay, we developed this technology called Nataraj. So basically the first Indian indigenous made legged robot system. So that was also one of our success stories. And there are other machines and prototypes developed after that, but the first one was Nataraj. We have something in laparoscopic and surgical units also. So many of these technologies that was done, we first experimented with a normal controller, normal systems, but then we moved to some kind of a remotized systems. So there are many areas where research do happen in our establishments, like modeling of joints of serial parallel robots. So joint is a very interesting structure. That means kind of a, you know, that gives basically the motion transmission systems and all. And modeling of gait of the legged robot, modeling of force and form closure of cooperative robot, modeling of cable-driven mechanism for surgical robots, and again the LabVIEW MATLAB augmentation. So this part we are very much stressing in our young engineers and scientists. Yes, you have to augment with some kind of a very well-known software platforms, and of course these days a lot of open source control algorithms are available. But this I am giving a glimpse when it was not so common. That is early 2000s and that kind of a period actually. Well, then let me take you to the next level of journeys of Department of Atomic Energy, where personally I am totally involved, and this is my project only. And for last 10 to 12 years, I am mostly engrossed with flexible robots developments, and basically these are for assistance and surveillance purposes, which Department of Atomic Energy needs it very badly. And from our initial development, some of the, not all, some of the flexible robots today, we have a kind of a remote control based systems also, starting from Wi-Fi, and also we have developed up to that level. Now there are indigenous hardwares and all design. So A to Z is kind of indigenous here. I can say it is my own, and some of my team members were also there. So first thing is DDFR, which is direct drive flexible robot. That means all these drives will be at a different joints only. That means directly we are controlling the joint of a flexible robot. As you can see in the picture, that upper one is a two-link kind of a flexible robot with a tapered joints. Of course, this is not drawn in scale. Then we have having FSFR type 1 and FSFR type 2. FSFR stands for flexible shaft driven flexible robot. So flexible shaft driven flexible robot means these joints are driven by some kind of a flexible shaft. So this is also an indigenous technology. Flexible shafts are available in commercial market. In fact, one US company is making, but it is very costly, and in fact for us it was not possible to procure. So we thought, and a lot of brainstorming happened, and then we could develop our own indigenous flexible shaft, which is a very another interesting story. Then we have PAR, patient assistant robot. Then we have SciPAR, sensor augmented intelligent patient assistant robot. We have few more, flexible universal modular robot. In fact, few more is just latest development. And Fsfr, which is still in the design stage, advanced design, I should say, flexible feeding assistant robot. So this is the total gamut of our flexible robot research, which started, like DDFR started around 2008-9, and then of course the other things started, and then latest is a few more we just completed in this year only. So this is a general picture, a kind of a conceptualization, schematic view of patient assistant flexible robot, and with a gripper. So this kind of a structure that we can have, and these joints, these motors are placed at the different joints. Of course, our prototype patient assistant robot is not with the motors at the joint. It was motors at the base, and then we can have it kind of a with flexible shaft. We are moving it actually. Now, from a theoretical point of view, there are many fundamental things associated with the flexible robot technology, because we have to design the link, we have to design the flexibility aspects, of course, how to control it. As you can know, this is very, very sleek and slender. So controlling that thing in real time is a big issue. And so that particular aspect is always haunted us. And we could, in fact, a lot of indigenous effort went to control this vibration of the flexible robot, and many theoretical paradigms modeling went to this structure actually. And here I am just giving some schematic diagram to show that how actually those cross section also changes. We can have a circular cross section of the flexible robot, we can have rectangular cross section, we can have some stepped configuration, etc., etc. So there are many variations that is possible. And so those gives details of our activity. And this particular structure having a kind of a tripod structure, and this tripod structure is basically giving you a kind of a vertical motion, so that you can adjust the height of the robot where it is working. As you can know that if it is a patient assistance system in say healthcare, in environment, hospitals and healthcare, we need to adjust the patient's, according to the patient's bed. This robot will be this thing. Even for surveillance also, we need to adjust the height, and we need to see the locations depending upon the structural things. And one important idea, I mean, that what I was telling, some of the photographic views are available with the DDFR type of things, which is our first development, and this was a very success story. And this particular joint assembly is being made. We have used follower Swiss miniature motor and the controllers also. So all those controllers, of course, those are bought out item, controller of the follower and the motor itself. because that time we were a little fortunate that embargo was partially withdrawn, so we could get some overseas motor. Of course, it is from Switzerland, so there was not much of a problem. But even then, we could do it. And this picture is showing the total prototype DDFR, and this DDFR is very, very long, 1.5 meter long. And in fact, we couldn't take a full picture that time, those days, because of technological limitations in VRC. So we could get part picture, and then finally we joined. And this particular structure has a good, very small miniaturized gripper, and that is also our own development and technological, kind of advancement, I should say. And in fact, every item of this particular DDFR was indigenous, and we are very proud to say that it has been developed, designed in India, developed in India, manufactured in some of the items in our premises, some of the items at vendor premises, but with our supervision. So we are very fortunate to have this thing. Now, with the success of DDFR, we moved to the FSFR type 1 and type 2. So the concept was, can we have some kind of a unification of the joint systems, and can we place the joint motor at the base itself? So that was the concept, because as you can see in the earlier version, and if we place the motor along with the link, that naturally the weight will increase, and that will cause more deflection or some other problem. So with that idea, our FSFR type 1 design came, and you can see these photographs are all inside our laboratories and work zones actually. So these motors were placed at the base, and then we could see the full things actually. And there was very miniaturized gripper at the end, and it was with a 3-link system. So we experimented a lot of things actually. And this FSFR type 2 was little more advanced, where we changed the material of link. See, in the FSFR 1, we used aluminium to have a proof of concept basically, whereas in FSFR 2, we have used the more lightweight but more strength material called CFRP, carbon fiber reinforced plastic, that was used. And we have my paper and other things there, and there you can get it. And even 2 YouTube videos are available where you can even see I think I will show the video also. So these are some of the details of this FSFR, and then we move to the next version, which is the PAR, which is patient assistant robot. Now in FSFR 2, whatever the problems we faced in PAR, we have removed, and basically in the PAR we have actually moved with a kind of a technology for its tripod mechanisms and its vertical up-down motion. So that was the criteria where we could concentrate more on that, and also our indigenous controller. So that was the difference between FSFR 2 and PAR. So these are all chronological. Actually, one after another we started, and we conceptual. As I was telling you, the DDFR program started around 2008-9, and then we experimented, and all those things happened. And then we slowly moved to FSFR type 1. But there was a considerable gap because we were not very sure how to get the flexible shaft, and it was not available those days, as I was mentioning. So some time was lost in that. Anyway, but then we pick up, and I think 2015 onwards, we could get all the materials, and we started again with a full pace. And this is today's prototype of PAR, patient assistant robot, which is fully operational, functional in our laboratories. And this is the complete prototype, which has got a YouTube video also. And there was a technology partner in Pune who has helped us in developing the full system based on our design and parameterization. And with the PAR, success of PAR, I should say, the working prototype, we moved to another interesting project in later part of 2018 actually. This is called SciPAR, which is Sensor Augmented Intelligent Patient Assistant Robot, and lot of modeling went actually. This prototyping is in progress right now, but we have changed several items actually, from the joint to many other small things to make it more versatile, more receptive. And it is intelligent in the sense that we have designed many sensors of that. So because it depends on the technology. Now we are having a lot of advances in sensor technologies, controller technologies, software. So those aspects are also come in the picture, and the augmentation becomes a reality actually. So we are taking help of that. So from the simple joint of our joint design, we move to many advancement of the Revolute joint here. Even the gripper, etc., is being changed. The scheme for strain gauge instrumentation. So instrumentation part is more in this SciPAR version compared to mechanical. Mechanical is more or less the same as PAR, with minor modifications in joints and other things. But main thing is the sensor instrumentation. Basically, we have mastered the technology of strain gauge instrumentation over the years, and this is quite our own indigenous things. And with the presence of LabVIEW softwares, so we could do all the calculations and so deflection measurement and all. So those things are done. And for gripper also we have done many things. This is a conceptual sketch of our latest flexible robot called FUMOR, Flexible Universal Modular Robot. In fact, this is already made now. So basically the idea is with a totally universal, totally flexible kind of a gooseneck link system we have used, and we wanted to try for a single link first with a gripper and how it performs, so that we can bend the link as per our wish. So these are all for some applications where we need little more careful applications, and these are small in size so that we can put it at different locations also. So with FUMOR, there are some changes in the joint housing and this tripod mechanism, even the solid modeling for the grippers, and there are some changes in the gripper also. So I'm not going to the details of that because it will take time. But basically, with some structural changes compared to PAR and SciPAR, in the FUMOR we could condition, and this is the one of the photographic view, and you can see the cuteness of this fellow. It is totally on the table, and it is very small but very effective in gripping and grasping actually. So this is our latest development, and another project which is already running in the as per the schedule is called Fsfr, which is Flexible Feeding Assistant Robot, and there are one or two designs available actually. So this is one design where we can have because this is based on the success of FUMOR, we could make it multi-joint or multi-link, you can say, multiple goose leg. So that was the idea, and that we can develop. And there are two designs basically. One is with the kind of a straight link for the gripper, another is for the moving flexible, again a flexible gooseneck link for the gripper, because we do not know how they will perform. And because of the gooseneck structure, there were some changes in the joint actually. So that is also very important. And basically the idea of flexible robots and their use in Department of Atomic Energy program is basically the gripping, because you know that worldwide in lot of laboratories flexible robots are studied, but they basically studied from the kind of academic point of view. But our application, our focus is on the application, and that is the reason we need grippers. But because of the size limitation, because of the weight limitations of the flexible robot, we need a gripper of very, very minute size, micro size, I should say, miniature size. And that is called SIMROG, which is sensor instrumented miniaturized robotic versions. We have version 1, and very recently version 2 is also we have developed. Now this is the SIMROG version 1. where we have, and it is a very, very small gripper. It is just 50 mm in length, 35 mm in width, and 15 mm in 35 mm in breadth, and 15 mm is the width. So you can see the tininess of the gripper. Yeah, there are many small grippers, as I was mentioning in the DDFR also. There is a small gripper, and that is also quite small, just like this Fsfr gripper. So DDFR gripper gave us a confidence that we can do some small business, actually, small manufacturing. Of course, there are a lot of difference between the manufacture. As you can see, the DDFR is almost 7-8 years ahead of Fsfr. So the manufacturing technology is different for DDFR. If I make the DDFR today, of course, there will be some advantage. Whereas in Fsfr, mainly the rapid prototyping things were used. So in the this flexible kind of a gripper system for DDFR, this has got its onboard controller here. So that is a good part, which was not there in Fsfr because of the size limitation, actually. Rather in DDFR, what we could use the extended portion of the gripper base plate, and we place the controller there itself. But at the same time, we could see the sensor length and all. So, that technology, time versus technology curve is important, actually. So we couldn't avoid a very small, long length of the sensors, which is not there in the case of our present thing. So this is another version of that DDFR gripper. Well, there are many research problems, which is because it is kind of an open system, and because I do give a lot of projects to the juniors. So modeling of joints of flexible robot is an interesting study that one can carry out. Modeling of the wrist of the flexible robot, that is also another interesting part. Kinematic analysis of flexible robots for real-time vibration, deflection, deformation studies. Flexible shaft-driven mechanism, how to model it, that is also very important. And also the software augmentation, because this time we need ANSYS FIST, that finite element softwares we need. ANSYS we all know, and FIST is our own homegrown software by ISRO. So both with ANSYS and FIST, and of course our lab systems are there. Let me move to the last segment, micro. This is the interesting part of DAE's program. We have developed a lot of robot grippers over the years, which are teleoperated, which are remote controlled, remotely operated. Many things are there, and there are several designs of the jaws, as you can see from a straight jaw kind of a system, which is my own design in during 2006-7, I believe. And then there are my recent developments with curvilinear jaw, with metallic, with non-metallic, another combination of metallic and non-metallic. Then this is the metallic. So these 4 jaws, 4 grippers with curvilinear jaw of different shape, size, and dimensions. Of course, I have developed those things. But starting point was this was my own drawing development kind of thing. And similarly for the straight jaw kind of thing also, we developed, this was the primary development of the micro gripper. As you can see that today's micro gripper, whatever photographic view I have shown in the earlier slide, this is the mother of that particular design, actually. So I thought of with this much of gear train. Anyway, so these are the things. And similarly for this straight jaw grippers also, several kinematic chains were studied. So this was all with our technology. And this gripper designs, there are gripper for small payload serial manipulator, gripper for parallel manipulator, and gripper for multi-segment compliant robot. So all those things. This is one of the robot that was developed around 2017. And this uses a curvilinear jaw and kind of a little bit of compliant robot, I should say. That is, some compliance is there in the link. So that was developed. I think some of the pictures I have already shown, but basically idea is these are all SIMROG version 1 in action. And we have replaceability of the grippers is also done. And external dimension is, as I was mentioning, very small. And Simlog version 2 is this picture, where this is the final prototype of the version 2, which is fully sensor instrumented. And with this small volume, we have used some 4 kind of sensors, and there was some structural models also, and with a slight increase in the length, which is 66 millimeter, width 44, and breadth is 15 mm. Breadth is same. So little increase in the width and length, we would have a payload capacity of 1 kg. We can start with all these developments, and these developments have a fully indigenous technology, and we have used those things. So I think these are some of the videos I can probably show you. So the compliant robot that I was mentioning, well, the second one is also another interesting compliant robot, but with a different, some modifications from the previous one. Here also chronological step I have showing. So these two grippers and these two robots rather, they are differing not only in the construction but control technology also. As you can see, much improvement in their gripping postures, and it can go to a much good height also. So those things are possible with developmental activities, and sometimes this is for our patient assistant robot, which is in the fully working prototype. Different motions will be shown here. And to tell you one interesting part, this is fully open loop control. most important part is the joint maneuverability and the programming aspect also, which is, as I was mentioning, fully indigenous. Well, so this is the thing, and this is our latest development, few more, which is just tested a month back by me, and it is a rush video. I mean, of course, not a fully professional level video, but I would like to show you that how it is happening. And you see it is already gripped on object, the yellow colored object, and this is a single link system, but with a bend. Like you can have a lot of bend possible in the gripper, sorry, in the flexible link. It's a gooseneck kind of a link. So this is our first attempt, and the gripper is having some kind of a novelty also compared to the earlier gripper. So this is the technology that we are already confident enough to go forward. There are again the lot of research problems that is possible. Similarly, the joints and wrist of the compliant robotic grippers, just like a flexible robot, in the grippers also we have a lot of mechanisms. In fact, those grippers are with a mechanism basically. Similarly, the vibration problem, modeling for the linkage driven mechanisms, and of course the software simulation and the finite element modeling. So those things are there. Now I will take you to the last part of the journey, which is basically future research. Now in the future research at DE, we have two major projects that has been thought of with my supervision. One is robotic surveillance of spent fuel storage bay pool with a customized report. Basically, the idea is a surveillance type of activity with a customized robotic system with a customized gripper in our atomic energy area. And project 2 is basically for social health care, which is design and development of a patient assistant flexible robot fitted with customized grippers. So based on our success of the PAR, now we are attempting for customized grippers. That means there will be a turret of kind of a system where multiple grippers will be there. So that was a project that has been conceptualized, and we are hopeful that we'll be doing. Now, the first one is basically we call CAR, Compliant Articulated Robot. So it is basically some kind of inspection system. So inspecting the tag number of the spane fuel rods. In fact, IAEA has a similar project, but they are not doing with the articulated robot. They are doing with some kind of a floating robot. And that was a very recent project they floated. And we want to estimate the overall thermal condition of the spent fuel, assessment of the remnant radioactivity, etc., etc. So this is the kind of thing. And very quickly, this is artistic view only, and these projects are already in the kind of a drawing boards level. And we could see the spent fuels, which is actually at the bottom of the bay, which is a kind of a water tank. You can say considered a large water body, large water tank. And this robot is a gantry type of systems which can slide over the wall, and then it can inspect, and it will have a radiation sensor and a camera system. So this is the kind of a modeling that have been attempted for. I mean, design model that has been attempted. And in case of passenger assistant robot, PAR, already we have seen the activity, so we are quite confident about the technology. Only thing, it needs more customization now. So with customized gripper, we have thought of to have this kind of thing. As I can show you here, this is a kind of a conceptualization that has been made with motors at the link itself this time. Okay, so this PAR, whatever we developed, the video you saw, that is with flexible shaft driven system, but this PAR with customized grippers, we will be having the motors at the link itself. So that is the difference. And also the other things like flexibility assessment, judgment, and modeling, those things will be more or less common, but we'll have, simple spring systems and also the spring dashboard based systems for modeling. So both of the systems will be trying. The conceptualization of the multi-gripper system is something like that. That means there will be some 3 grippers with a kind of a turret sort of a system. And this is the first time that we will be trying this thing. So we want to make a kind of a small test bed first, and then we'll go for it actually. So this is the plan as of now, but of course, this is a little futuristic. Maybe in another 5 to 7 years, we'll be able to show the real prototyping part of it. So this is the plans, and I am at the end. So thank you very much for your patient hearing. And idea is basically this is a novel research area, no doubt, in the domain of robotics. But remote control robotics is another area where, of course, Department of Atomic Energy can be the torch bearer. But nonetheless, we have a plan of collaboration with through different forums, including Department of Science and Technology, Government of India, and other forums, so that we can go ahead with more advancement in technology, more advancement in kind of a novelty of the systems. So with that, I am ending my lecture, and hope you have this thing. And in case of you have any questions, you can ask, or you can ask me afterwards through email also. Thank you very much.
Thank you so much, sir. Thank you for your very informative lecture, and really it is a motivating factor for many of us to do the research work. And now it is open to the participants. Please interact with our expert. And this is a good platform. You can interact with such an eminent person and develop your knowledge. It's a knowledge sharing session now. Please, any queries, any clarifications or any doubts are there, please clear now itself. Or you can mail to him with his permission. If you want, I will send the contact details.
Yes, no problem. My details are already available with many web resources also. So, Professor Devdas, you can kindly give my
Yes, sir.
email, both my BRC email and my Gmail to the participants in case they have some queries afterwards, or they want to have some kind of a guidance from me or some small collaboration in some form or the other. I will be very happy to like interact with them. In fact, I love students and young faculty so that I can mentor them. They are the next generation of our country.
Yes, sir.
So that will be my pleasure. Okay, I think then let me stop sharing the screen, and I think that will be the good.
Sir, if possible, some part of your lecture, please mail to me. I will. I could share it to the participants.
Okay, sure. I will, of course, size-wise, I have to check. I do not know really. But yeah, some part of the things I can probably convert to PDF and sort of things. And a couple of photographs and pictures are already there in some of my recent publications, and these things are there. But I will try to send a part of this lecture.
Thank you, sir.
Yeah, thank you very much. Okay, so I think may I then end the session, or because it is little late for
Yes.
me.
Yes, sir. Yes,
Because
sure,
we
sure.
could, yeah, I mean, maybe late for you all also.
Okay, sir.
Okay.
Once again, we thank. Yeah. Yes, yes. Please, Vinayak, please. Any question?
Hello, sir. I'm having one question.
Yes, please.
So, if considering the master-slave architecture, as the slave is going to be used inside a hot cell, so what kind of a material is going to be used to build the slave?
These are all various grades of stainless steel only. We have some particular customized grade actually. That details I cannot divulge because of the security issues. But grossly speaking, these are some metallurgical variants of stainless steel only. But some special kind of thing, which we do make in the sense that we do order to a particular government organization for supplying to DAE.
Okay, sir. Okay. Thank you.
See, hot means, as I was mentioning, it is not temperature-wise very hot.
No.
It is
It's
actually radiation-wise.
the
So
radiation,
basically,
right?
radiation resistant. Because the radiation resistance is available, and this is our own indigenous. I mean, in India only you can get it, no problem. So those things get supplied, and then our workshop, central workshop of Department of Atomic Energy, which is situated in Mumbai in Bark campus only, and that is a kind of a centralized agency who develop all these kind of components. Sometimes we do give to a vendor also. So we have a MU with that particular party, and they also develop on behalf of us many times.
Okay. Thank you.
Okay, thank you very much.
Okay.
Thank you.
Thank you, sir. So, on behalf of the organizing team and the Vimal Jyoti Engineering College, I thank you. Thank you for sparing your wonderful time with us. Thank you. Thanks a lot, sir.
Thank
Good
you,
night.
Professor. Thank you, Professor. Yeah, it is a good opportunity for me to interact, and hopefully we'll get a chance to meet
Sure, sir.
all of you physically after this pandemic overs. Okay, thank you very much.
Sure, sir.
Okay,
Thanks a
good
lot.
night.
Okay.
Good night.
Good night. Dear participants, this is the end of the third day of our FDP, and we will meet tomorrow morning as usual. Okay. Thank you all. Stay safe. Good night to all.
என்ன பண்றேன் ஃபீட்பேக் ஃபார்ம்